Tonight, we begin a gentle journey into one of the most beautiful truths the universe has ever whispered to us. A truth so profound that it reshapes how we see ourselves, our place in the cosmos, and the very substance of our being. It is this: you are made of stars, not metaphorically, not poetically, but literally, physically, atom by atom. The calcium in your bones, the iron in your blood, the carbon that forms the architecture of every cell in your body, all of it was forged in the heart of a dying star, scattered across the cosmos in a final, brilliant explosion, and gathered here, billions of years later, into the intricate pattern that is you. There is something almost dreamlike about this realization, isn't there? Something that makes the boundary between self and universe feel suddenly permeable, like mist dissolving in morning light. When you lift your hand before your eyes, you are not simply looking at flesh and bone, you are gazing at stardust, at atoms that have traveled across unimaginable distances and incomprehensible stretches of time to be here, now, arranged in this particular configuration that thinks and feels and wonders about its own origins. The story begins, as so many cosmic stories do, with hydrogen, the simplest, most abundant element in the universe, born in the first few minutes after the Big Bang. For hundreds of millions of years, the universe was filled with vast clouds of this primordial hydrogen, drifting through darkness, cold and undifferentiated. But gravity, patient and inexorable, was already at work, pulling these clouds together, compressing them, heating them. And when the pressure and temperature grew intense enough, something remarkable happened. The hydrogen began to fuse, forming helium and releasing tremendous energy in the process. The first stars ignited, and the universe blazed with light. Yet these early stars could only make the lightest elements, the periodic table we know today, with its dizzying array of substances: oxygen and nitrogen, silicon and sulfur, gold and silver, and everything in between. None of this existed yet. The universe was made of little more than hydrogen and helium, like a painter with only two colors on their palette. Everything else, every element heavier than helium, would have to be made inside stars, and not just inside them, but through their deaths. Picture yourself for a moment in the quiet of this evening, breathing slowly, feeling the rise and fall of your chest. That oxygen you're breathing, created in a star, the nitrogen that makes up most of the air around you, stellar origin, the carbon dioxide you exhale, carbon from ancient stellar furnaces, combined with oxygen from others. With every breath, you are cycling elements that were once at the core of massive suns, subjected to pressures and temperatures beyond imagination, transformed through nuclear alchemy, and then cast out into space in catastrophic explosions that could outshine entire galaxies. And in this, there is a curious comfort. We often think of ourselves as separate from the universe, as observers standing outside of nature, looking in. But the evidence written in our very atoms tells a different story. We are not separate from the cosmos. We are the cosmos, localized, condensed, made aware of itself. The same laws of physics that govern the death of stars also govern the beating of your heart. The same fundamental forces that shaped the universe in its first moments continue to hold together the molecules of your being. This connection runs deeper still. Every atom in your body is ancient beyond reckoning. The hydrogen in your water may have been formed shortly after the Big Bang itself, nearly 14 billion years ago. The heavier elements, the calcium, the iron, the zinc, are younger, but still incredibly old, forged in stellar cores that burned and died long before our sun was born, long before the Earth coalesced from cosmic dust. These atoms have been recycled countless times, through multiple generations of stars, through nebulae and planets, through ancient seas and primordial atmospheres. There is a particular iron atom in your blood right now, one of the billions carried by hemoglobin through your veins, delivering oxygen to your cells. That atom was once at the heart of a massive star, part of the star's final, desperate attempt to sustain itself through fusion. When that star could fuse no more, when its core collapsed and rebounded in a supernova explosion, that iron atom was hurled into space at tremendous velocity. It drifted through the galaxy for millions or billions of years, eventually finding its way into the cloud of gas and dust that would become our solar system. It was incorporated into the early Earth, cycled through geological processes, perhaps dissolved in ancient oceans, taken up by primitive life forms, passed through countless organisms over billions of years, and finally arrived in your body, where it carries oxygen, enabling every thought, every breath, every moment of your existence. This is not merely a scientific fact, it is a kind of secular sacrament, a revelation that places us firmly within the grand narrative of cosmic evolution. We are not visitors to this universe, we are made of it, through and through. The universe has been working for billions of years to create the conditions for your existence, gathering elements from dying stars, assembling them into planets, nurturing the emergence of life, leading through vast chains of evolution to this moment, to you, reading these words, contemplating your own cosmic heritage. As we drift deeper into this exploration of supernovas and stellar death, carry this awareness with you. We are seeking to understand not just distant astronomical phenomena, but the very process that made us possible. We are, in a very real sense, the universe trying to understand how it creates complexity, how it makes meaning, how dying stars give birth to life. There is something profoundly humbling and profoundly elevating about this. Perspective humbling because it reminds us how small we are in space and time. Elevating because it reveals how deeply we belong to something vast and ancient and ongoing. The atoms in your body have witnessed the birth and death of stars. They carry within them the memory of cosmic violence and cosmic creation, and now they are here, arranged in the pattern of you, enabling you to wonder, to question, to seek understanding. In learning about supernovas, we are, in a sense, learning our own origin story, not the proximate story of human evolution or even the formation of Earth, but the deeper story, the atomic story, the story written in stellar fire and scattered through the cosmic dark, waiting to be gathered into new forms, new possibilities, new expressions of the universe's endless creativity. In the quiet depths of space, scattered across hundreds of billions of galaxies, there burn countless furnaces, not furnaces of metal and fire as we know them, but vast spheres of plasma where matter transforms itself through processes of stunning violence and exquisite precision. These are stars, and they are nothing less than the alchemical laboratories of the cosmos, the only places in nature where new elements are born. To understand how stars create elements, we must first understand what stars are not, as the twinkling points of light we see on a clear night, romantic and distant, but as they truly exist, massive gravitational prisons where matter is compressed and heated to such extremes that the fundamental rules of atomic interaction are overcome. At the core of a star, hydrogen nuclei, simple protons, are forced so close together, under such tremendous pressure and temperature, that they overcome their natural electromagnetic repulsion and fuse, joining to form helium and releasing energy in the process. This is fusion, the power source of stars, the mechanism that has kept our own sun burning for nearly 5 billion years and will sustain it for 5 billion more. It is, in many ways, a precarious balance, a tug of war between gravity, which wants to crush the star inward, and radiation pressure, which pushes outward from all those fusion reactions in the core. As long as fusion continues, as long as the star has fuel to burn, this balance holds. The star shines steadily, a beacon of stability in the chaos of the cosmos. But here is where the story becomes truly interesting, where we begin to see how stars build the periodic table, element by element, like patient craftsmen working with the most fundamental materials of reality. In the earliest moments of the universe, in the 3 minutes following the Big Bang, only the lightest elements were formed, mostly hydrogen, some helium, traces of lithium. Everything else, every element heavier than these primordial three, has been forged inside stars or in the violent deaths of stars. Let us follow the process, step by gentle step, as it unfolds over millions of years inside a stellar core. The star begins its life, fusing hydrogen into helium. 4 hydrogen nuclei combining through a series of steps to form one helium nucleus. This helium, slightly heavier than hydrogen, begins to accumulate at the star's core. For stars like our Sun, this hydrogen fusion will continue for billions of years, a slow and steady burn that provides stable light and warmth to any planets fortunate enough to orbit at the right distance. But for more massive stars, those born with many times the mass of our Sun, the story unfolds more quickly and dramatically. These stellar giants burn through their hydrogen fuel in mere millions of years rather than billions, living fast and bright. And when the hydrogen in their cores is exhausted, when there is nothing left but helium ash from billions of years of fusion, something remarkable happens. The core contracts, compressed by the weight of the star's outer layers. Temperature and pressure rise, and at a certain threshold, a new kind of fusion ignites. Helium burning, 3 helium nuclei, each with 2 protons, fused together in a delicate dance to form carbon, the foundation of all life as we know it, the element that forms the backbone of organic chemistry, the substance of which you are primarily made. It is both humbling and beautiful that the carbon in your DNA, in your proteins, in every organic molecule of your being, was forged through this helium fusion in the cores of ancient stars that died before our solar system was born. Meanwhile, across the vast expanse of the star's interior, the process continues. As the helium burns and forms carbon, some of those carbon nuclei capture additional helium nuclei, forming oxygen, the element you are breathing right now, the element that makes up most of the mass of water, the element essential to almost all life on Earth. And so the star builds, layer by layer, a kind of cosmic onion, with different fusion processes occurring at different depths, each producing its own characteristic elements. Yet this is only the beginning of the story. In the most massive stars, those with 8 or more times the mass of our Sun, the process continues beyond carbon and oxygen. As each fuel is exhausted, as each new element accumulates in the core, the temperature and pressure rise further, allowing new fusion reactions to ignite. Carbon fuses with carbon to produce neon and magnesium. Neon burns to create oxygen and magnesium. Oxygen fuses to produce silicon and sulfur. There is something almost musical about this progression, a rhythm of creation and exhaustion, burning and cooling, that builds the elements in a specific sequence determined by the fundamental laws of nuclear physics. Each stage produces the fuel for the next stage, like a carefully orchestrated symphony where each movement sets up the next, building toward a dramatic crescendo. The star, in its later stages, develops a layered structure of stunning complexity. At the outermost layers, hydrogen still burns, perhaps in a shell around the core. Beneath that, a helium-burning shell. Deeper still, shells of carbon burning, then oxygen, then silicon, each layer producing its own characteristic elements, each operating at its own temperature and density. It is like a cosmic factory with multiple assembly lines running simultaneously, each producing different products from different raw materials. And here is where we begin to glimpse the profound importance of stellar evolution for our own existence. Without these fusion processes, without the patient accumulation of elements inside stellar cores, the universe would remain forever composed of only hydrogen and helium. There would be no carbon for organic chemistry, no oxygen for respiration, no silicon for rocks, no iron for planetary core, no calcium for bones, no phosphorus for DNA. The rich complexity of the material world, the very possibility of chemistry as we know it, depends entirely on the nuclear reactions occurring inside stars. Consider the silicon in the computer or phone you might be using to read these words, or in the sand beneath your feet, or in the rocks of mountains. That silicon was forged through oxygen fusion in the heart of a massive star. The phosphorus that forms the backbone of your DNA, carrying genetic information from one generation to the next, was created through similar high-energy fusion reactions. Every element around you, every substance you touch, every atom in your environment, save for the primordial hydrogen and helium, all of it came from stars. But there is a limit to this process, a fundamental constraint imposed by the laws of physics. Fusion releases energy only when it combines lighter elements into heavier ones, up to a point. That point is iron. Iron has the most stable nucleus, the configuration of protons and neutrons, with the lowest energy state. Fusing elements lighter than iron releases energy. Fusing elements heavier than iron requires energy. For a star, this is a catastrophic limitation. When the core of a massive star begins producing iron, when iron accumulates at the very center where the temperature and pressure are highest, the star has reached the end of the line. There is no fusion reaction that can tap iron for energy. The star's power source shuts down. And in that moment, after millions or even billions of years of stable burning, everything changes. The careful balance between gravity and radiation pressure collapses. The core, no longer supported by the outward push of fusion energy, begins to fall inward under its own tremendous gravity. This is the prelude to death, the moment when the stellar forge that has been building elements so patiently is about to become something else entirely. Not a forge, but a cosmic crucible, a furnace of such intensity that it will create in seconds what the star could not create in millions of years of stable burning. The iron core, that final product of fusion, becomes the seed of destruction. And yet, as we shall see, This destruction is also the ultimate act of creation, the moment when the heaviest elements are born and scattered to the cosmos, the moment when the star's death becomes the source of future life. There is something profoundly calming about understanding the life cycle of stars, perhaps because it reminds us that even on cosmic scales, there are patterns, rhythms, a kind of natural order to the way matter organizes and reorganizes itself across the vast stretches of space and time. Stars are born, they live, they die, and in dying, they give birth to new possibilities. It is a cycle as fundamental as the seasons on Earth. Though operating on timescales that dwarf human comprehension, a star's story begins not in fire, but in cold. Scattered throughout every galaxy are vast clouds of gas and dust, nebulae of hydrogen and helium left over from the Big Bang, enriched with heavier elements from previous generations of stars that have lived and died. These clouds drift through space, dark and quiescent, sometimes for millions of years, seemingly inert. But within them, gravity is always at work, patient and inexorable, pulling matter together, creating slight irregularities in density, regions where the gas is just a bit more concentrated than elsewhere. These dense regions pull in more material, growing slowly at first, then faster as their gravitational influence strengthens. The cloud begins to collapse inward, falling into itself. As it falls, the gas compresses and heats, transforming gravitational potential energy into thermal energy. What was once spread across light years begins to concentrate into a region perhaps only a few times larger than our solar system. The pressure and temperature at the center rise steadily, hundreds of degrees, then thousands, then hundreds of thousands. Then, when the core reaches about 10 million degrees Kelvin, something miraculous happens. Hydrogen nuclei, smashed together by the immense pressure, overcome their electromagnetic repulsion and fuse. The thermonuclear reactions begin. Light bursts forth. A star is born, a new light in the cosmos, taking its place among billions of others, in an ongoing cycle of stellar birth and death that has been occurring for over 13 billion years. For most stars, like our own Sun, this marks the beginning of a long and stable life. The star settles into what astronomers call the main sequencer phase, where hydrogen fusion in the core provides a steady output of energy that balances the inward pull of gravity. The star will remain in this state for billions of years, barely changing, a reliable beacon shining across the light year. Around such stars, planets can form, atmospheres can develop, oceans can fill, and perhaps given enough time and the right conditions, life can emerge and evolve. But the mass of a star at birth determines not just how long it will live, but how it will die. Loma stars, though smaller than our Sun, burn their fuel so slowly, so miserly, that they can shine for tens or even hundreds of billions of years longer than the current age of the universe. These red dwarfs will outlive everything, burning steadily into an unimaginably distant future. Long after larger stars have exhausted themselves and died, they will end not in spectacular explosions, but in slow fading, gradually cooling into darkness over eons. Stars like our Sun, medium-sized and moderate in temperament, will burn for about 10 billion years in total. In roughly 5 billion years, our Sun will exhaust the hydrogen in its core, unable to maintain the fusion that has supported it for so long. The core will contract and heat, while the outer layers will expand dramatically. The Sun will become a red giant, swelling until it perhaps engulfs the inner planets, including Earth. Eventually, it will shed these outer layers in beautiful, glowing shells, planetary nebulae. Though they have nothing to do with planets, while the core collapses into a white dwarf, a dense ember slowly cooling over trillions of years. Yet this is only the beginning of understanding stellar death, because the most massive stars, those born with 8, 10, 20, or even 100 times the mass of our Sun, follow a very different path. A path that leads not to gentle fading but to cataclysmic explosion. And it is these massive stars, these cosmic giants, that concern us most in our story, because it is through their violent deaths that the heaviest elements are created and scattered. Through space, a massive star lives fast and burns bright, with much more fuel to burn, but also much more gravitational pressure forcing fusion to occur at breakneck rates. These stars consume their hydrogen in mere millions of years rather than billions. But unlike smaller stars, when a massive star exhausts its core hydrogen, it doesn't begin a long, slow decline. Instead, it enters a new phase, igniting helium fusion, then carbon fusion, then neon, then oxygen, then silicon, building layer upon layer of different elements, each shell fusing its own fuel, each producing the seeds for the next stage. This is the stellar onion we encountered in our last exploration. Hydrogen fusion surrounding shells of helium fusion surrounding carbon burning, and on down through the periodic table. But each successive stage lasts for less time than the previous one. A massive star might spend 1,000,000 years burning hydrogen, 100,000 years burning helium, 1,000 years burning carbon, a few years burning oxygen. Silicon fusion, the final stage that produces iron, might last only days or weeks. As we drift deeper into this understanding, we can see the star racing toward an inevitable conclusion. Each stage produces elements that cannot be further fused for energy. The star builds toward iron, toward that most stable of nuclei, toward the element that marks the end of fusion's power to sustain stellar life. The iron core grows, fed by the silicon fusion shell above it. It might reach a mass comparable to our entire sun, yet be compressed to a sphere only a few thousand kilometers across, with density so extreme that a teaspoon of the material would weigh as much as a mountain. And here, in the accumulation of iron in the core, we find the seed of catastrophe. The star has been playing a balancing game for its entire life. Radiation pressure pushing out, gravity pulling in, the two forces in equilibrium. But iron fusion cannot add to that radiation pressure. Iron is an energy sink, not an energy source. When silicon stops fusing because it has all been converted to iron, when the iron core has nothing left to fuse, the radiation pressure that has been holding up the star suddenly disappears. The core, no longer supported, begins to collapse. Not slowly, not gradually, but catastrophically fast. In less than a second, the core implodes, matter falling inward at velocities approaching a significant fraction of the speed of light. The iron nuclei, subjected to such tremendous pressure, begin to break apart in a process called photodies. The very elements that the star spent its entire life building are being torn back, apart into their constituent protons and neutrons. Electrons are forced into protons, creating neutrons and releasing neutrinos in a flood that carries away tremendous energy. The core collapses until it reaches densities comparable to an atomic nucleus, the entire mass of a sun compressed into a sphere perhaps 20 kilometers across. At this point, the matter becomes the collapse suddenly halts, and like a rubber ball smashed against an infinitely hard floor, it rebounds. A shockwave forms and races outward through the star's layers at thousands of kilometers per second. This shockwave encounters the shells of heavier elements surrounding the core, the silicon, the oxygen, the carbon, the helium, the hydrogen. In the intense heat and pressure of the shockwave, a final burst of fusion occurs, creating elements heavier than iron in seconds. The shock reaches the star's surface and breaks through. The star explodes. This is a supernova, one of the most energetic events in the universe. An explosion so powerful that for a brief period, the dying star can shine as brightly as an entire galaxy of hundreds of billions of stars. The outer layers of the star, enriched with all the elements created during its life and in the final moments of explosion, are hurled into space at tremendous velocities. Gases and dust expand outward, mixing with the interstellar medium, enriching the galaxy with heavy elements. Perhaps the most beautiful aspect of this cosmic violence is its creative power. In dying, the star scatters the elements it created across light years of space. These elements, forged in nuclear fire and dispersed by explosive death, drift through the galaxy, eventually mixing with clouds of primordial hydrogen and helium. When these enriched clouds collapse to form new stars and planetary systems, they carry within them the periodic table of elements: carbon, oxygen, silicon, iron, and all the others, the chemical ingredients necessary for rocky planets, for water, for the complex chemistry that makes life possible. Every element heavier than helium in your body, every atom of carbon and nitrogen and oxygen, every trace of iron and zinc and copper, came from a star that died before our sun was born. Your very existence depends on stellar death, on the willingness of nature to destroy one generation of stars so that new possibilities can emerge. In this cycle of birth and death, of creation and destruction, the universe builds complexity, layer by layer, generation by generation. And in this dance of stellar life and death, we find ourselves made of stardust, children of stellar explosions. The universe's way of knowing itself, carrying within our bodies the memory of cosmic violence and cosmic creation. forever connected to the vast cycles that turn across the depths of space and time. For much of human history, the stars were mysteries written in light against the darkness, beautiful, distant, seemingly eternal, but fundamentally unknowable. Ancient peoples wove them into myths and legends, seeing in their patterns the shapes of heroes and beasts, using their positions to navigate seas and mark the passage of seasons. But the question of what stars actually were, what they were made of, and how they produced their light remained beyond reach, hidden behind the vast gulf of space that separated us from them, even into the early 20th century. As physics was being revolutionized by quantum mechanics and relativity, the composition of stars remained mysterious. Scientists knew they were hot, knew they were massive, knew they were made primarily of hydrogen. By the 1930s, physicists had worked out that fusion, the combining of hydrogen nuclei to form helium, could power stars, solving the puzzle of how they could burn for billions of years without exhausting their fuel. But the deeper question, the question of where all the other elements came from, remained unanswered. Some scientists proposed that all the elements had been created in the first moments after the Big Bang, forged in the primordial heat of the universe's birth. This was a tidy theory, one that required no special pleading, no additional mechanisms beyond the initial cosmic explosion. But as understanding of nuclear physics deepened, problems emerged with this picture. The early universe had been hot enough and dense enough to fuse hydrogen into helium, yes, and to create traces of lithium, but it cooled too quickly, expanded too rapidly, to build the heavier elements. There was a gap, a missing mechanism, a puzzle that needed solving. The answer came through the work of several brilliant minds working in the 1950s. Though, like many great scientific insights, it emerged gradually, piece by piece, rather than in a single flash of revelation. The key figure in this story is Fred Hoyle, a British astronomer with a talent for both rigorous calculation and colorful communication. Hoyle, working at Cambridge University, became convinced that stars were not just burning hydrogen, they were cosmic factories, manufacturing the entire periodic table of elements through nuclear reactions in their interiors. Hoyle was joined in this work by a remarkable team: Margaret and Geoffrey Burbidge, a husband and wife duo whose partnership in both science and life would prove extraordinarily fruitful, and William Fowler, an American nuclear physicist who brought deep expertise in the experimental measurements of nuclear reaction rates. Together, these four would produce one of the most important papers in the history of astronomy, so influential that it's still known simply by the initials of its authors, BYFH. Published in 1957, there is something almost musical about how they worked through the problem. Margaret Burbidge brought observational astronomy, the careful measurement of which elements appeared in which stars. Geoffrey Burbidge contributed theoretical physics, the mathematical framework for understanding stellar structure. Fowler provided the nuclear physics data, the precise measurements of how nuclei interact and fuse, and Hoyle wove it all together. With his deep physical intuition and his conviction that stars must be the source of the elements. Their paper, formally titled Synthesis of the Elements in Stars, ran to over 100 pages of dense scientific reasoning. It laid out, step by methodical step, how stars could build the periodic table through a series of nuclear reactions. They showed that as a star ages and exhausts its hydrogen fuel, its core contracts and heats, allowing helium fusion to begin. They demonstrated how this helium burning produces carbon and oxygen, the foundations of terrestrial chemistry. They traced the process through successive stages: carbon burning, neon burning, oxygen burning, silicon burning, each producing heavier elements, each requiring higher temperatures and densities. But perhaps most remarkably, they showed how the heaviest elements, those beyond iron that cannot be produced through normal fusion, could be created in the extreme conditions of stellar explosions. They identified two processes: the S process, or slow process, where nuclei capture neutrons one at a time over long periods in stable stars, and the R process, or rapid process, where an overwhelming flood of neutrons is captured in seconds during supernova explosions. Through these mechanisms, they could account for essentially every element in the periodic table. Meanwhile, across the expanse of scientific geography, working independently at the Chalk River Laboratories in Canada, physicist Alistair Cameron was arriving at similar conclusions through different paths. Cameron published his work on stellar nucleosynthesis in the same year, 1957, approaching the problem from a more astrophysical angle. focusing particularly on supernova explosions. The convergence of these independent lines of research strengthened the case enormously when different scientists, working separately with different methods, arrive at the same conclusion. It suggests they're touching something real, something fundamental about the way nature works. The impact of this work rippled through astronomy and physics like waves across still water. It meant that the universe had a history, a developmental arc. The early universe was simple, mostly hydrogen and helium. But as stars formed, burned, and died, they enriched the cosmos with heavier elements. Each generation of stars was born from gas clouds, slightly more enriched than the previous generation. The universe was becoming more chemically complex over time, building toward the possibility of planets, of chemistry, of life. It also meant that we could read the history of the cosmos in starlight by carefully analyzing the spectrum of light from distant stars. The precise wavelengths they emit or absorb. Astronomers could determine which elements those stars contained and in what proportions. Older stars, formed early in the galaxy's history, showed less heavy elements. Younger stars, like our Sun, showed more. It was like reading tree rings, but instead of counting years, astronomers were reading billions of years of galactic chemical evolution. Fred Hoyle, with characteristic eloquence, captured the profound implications of this discovery in a series of public lectures. He spoke of how every person contains atoms that were once inside stars, how the iron in our blood and the calcium in our bones were forged in stellar furnaces billions of years ago. He painted a picture of cosmic connection, of deep time written in our very substance. Though Hoyle never received the Nobel Prize for this work, a controversial omission that many felt was unjust, his insights permanently changed how we understand our place in the universe. Margaret Burbidge, one of the few women working in astronomy at the highest levels during this era, would go on to have a long and distinguished career, breaking barriers and mentoring future generations of astronomers. Her contributions to understanding stellar nucleosynthesis were foundational, yet she faced discrimination and obstacles throughout her career simply because of her gender. When she was appointed the first female director of the Royal Greenwich Observatory in 1972, it was both a recognition of her brilliance and a reminder of how slowly institutions change. As we drift forward from this moment of discovery, carrying with us the understanding that stars create elements, we can appreciate how science builds knowledge gradually, brick by brick, insight by insight. The story of stellar nucleosynthesis wasn't discovered in a single moment of genius, but emerged through the patient work of many minds, checking and cross-checking each other's calculations, building frameworks to contain and explain observations, always asking, how does nature accomplish this? What are the mechanisms? What does the evidence really tell us? And in answering these questions, they revealed something beautiful. The stars are not merely distant lights, but active participants in cosmic evolution, engines of creation that had been steadily enriching the universe with complexity for billions of years, making possible the chemistry of life, the formation of planets, and ultimately, the emergence of beings who could look back at the stars and understand, at last, where they themselves came from. Picture, if you will, the interior of a massive star in its prime, not as a uniform sphere of burning gas, but as a kind of cosmic architecture, a structure built from concentric shells, each with its own temperature, its own density, its own nuclear reactions producing its own characteristic elements. This is stellar structure at its most complex and beautiful, a testament to how gravity and nuclear physics conspire to create order, even in the heart of stellar fire. At the very center lies the core, the hottest and densest region, where the most energetic nuclear reactions occur. In a young massive star, this core is fusing hydrogen into helium through the proton-proton chain, or more commonly in massive stars, through the CNO cycler process that uses carbon, nitrogen, and oxygen as catalysts to convert hydrogen into helium more efficiently. The temperature here might reach 15 or 20 million degrees Kelvin, hot enough that the hydrogen nuclei collide with sufficient energy to overcome their electromagnetic repulsion and fuse. This hydrogen burning continues for the longest portion of the star's life. For a star 20 times the mass of our Sun, this phase might last 5 or 6 million years, brief by cosmic standards, but stable, steady, a time when the star maintains its equilibrium and shines with consistent brightness. The helium produced by this fusion accumulates in the core, like ash from a fire, gradually displacing the hydrogen fuel. And then comes a moment of transition, subtle at first, but profound in its implications. The hydrogen in the core is exhausted, no longer supported by fusion energy pushing outward. The core begins to contract under its own gravity. As it contracts, it heats, a fundamental consequence of gravitational compression, transforming potential energy into thermal energy. The temperature rises from 20 million degrees to perhaps 100 million degrees. At this threshold, a new reaction becomes possible. Helium fusion. 3 helium nuclei, each containing 2 protons and 2 neutrons, come together in a delicate process called the triple alpha reaction, so named because helium nuclei are also called alpha particles. Two helium nuclei briefly fuse to form berylliumate, an unstable isotope that normally decays almost instantly. But if, in that brief moment before decay, a third helium nucleus collides with the beryllium, they fuse to form carbon-12, a stable isotope that will persist. It is an improbable process, requiring 3 particles to come together in just the right way at just the right moment, and yet it happens, trillions upon trillions of times per second in a stellar core, building up carbon atom by atom. Some of this carbon captures additional helium nuclei, forming oxygen-16, and so the star begins to manufacture the 2 elements most essential for life as we know it, the foundation of organic chemistry, the element that can form the complex molecules necessary for biology, and oxygen, the element we breathe, the element that makes up most of the mass of water, the element without which terrestrial life would be impossible. There is something profoundly moving about this realization. The carbon in your DNA, in your proteins, in every organic molecule of your being, was created through this triple alpha process in stars that died billions of years ago. The oxygen you breathe with every inhalation came from the same stellar cores, captured by helium nuclei and preserved through the violent dispersal of stellar explosions. Life, in a very literal sense, is built from the ashes of dead stars. As helium burning proceeds, the structure of the star becomes more complex. Hydrogen fusion doesn't stop entirely, it continues in a shell surrounding the helium burning core. A shell where the temperature is still high enough for hydrogen to fuse, but not yet high enough for helium to burn. The star now has a layered structure, a carbon-oxygen core, growing steadily larger, surrounded by a helium-burning shell, surrounded by a hydrogen-burning shell, surrounded by the vast outer envelope of the star, where temperatures are too low for any fusion to occur. Meanwhile, in the most massive stars, those with more than 8 times the Sun's mass, the process continues into even more exotic realms of nuclear physics. The carbon-oxygen core grows until it reaches a critical mass and temperature. The core contracts again, heats again, and reaches about 600 million degrees Kelvin, hot enough for carbon fusion to ignite. Carbon nuclei fuse together through various reaction pathways, producing neon, sodium, and magnesium. Some reactions release protons or alpha particles that are captured by other nuclei, creating a complex web of nuclear transformations. The stellar core is becoming a kind of cosmic chemistry set, where the rules of terrestrial chemistry no longer apply, where atomic nuclei combine and recombine in patterns determined purely by nuclear physics and the extreme conditions of temperature and pressure. This carbon burning phase lasts perhaps 1,000 years long by human standards, but merely a blink in the life of the star. When the carbon is exhausted, the core contracts once more, heats once more, and at about 1.2 billion degrees, neon begins to burn. Neon fusion produces oxygen and magnesium, adding to the growing repository of heavy elements in the stellar core. This phase lasts only about a year. Then comes oxygen burning at about 1.5 billion degrees, producing silicon, sulfur, and other elements in the middle of the periodic table. This phase lasts perhaps 6 months. The star is accelerating toward its doom, each successive phase of fusion occurring faster than the last, producing less energy, sustaining the star for briefer periods. By this point, the star's internal structure has become extraordinarily complex. Imagine cross-sectioning this stellar giant, slicing it open to reveal its layers like a cosmic onion. At the outermost layers, hydrogen is still fusing, producing helium. Deeper in, a helium shell burns, producing carbon and oxygen. Deeper still, a carbon-burning shell produces neon and magnesium. A neon-burning shell produces oxygen and magnesium. An oxygen-burning shell produces silicon and sulfur. And at the very center, the newest process is about to begin: silicon burning. Silicon burning occurs at temperatures above 3 billion degrees Kelvin. At these extreme temperatures, photons have so much energy that they can break apart nuclei that were previously stable. Silicon nuclei break apart and recombine in complex sequences, gradually building heavier and heavier elements. First scandium and titanium, then chromium and manganese, then iron, cobalt, and nickel. The reactions proceed through photodisintegration and recombination, a kind of nuclear alchemy driven by pure thermal energy. This final phase, this silicon burning that produces iron group elements, lasts only days or weeks. The star, which spent millions of years burning hydrogen, now races through its final nuclear fuels in a cosmic sprint toward catastrophe. The iron core grows rapidly, fed by the silicon burning shell above it, accumulating mass at the rate of solar masses per day. And here, in this iron core, we find the boundary between possible and impossible, between energy source and energy sink, between stellar life and stellar death. Iron represents the most stable configuration of protons and neutrons. Fusing lighter elements into iron releases energy, but fusing iron into heavier elements requires energy. It's an endothermic process, one that consumes energy rather than producing it. For a star that has maintained its structure through the outward pressure of fusion energy, this is a catastrophic limitation. As we drift toward understanding the significance of iron, we can appreciate the extraordinary journey the star has undertaken. From simple hydrogen, through helium, carbon, oxygen, neon, magnesium, silicon, sulfur, and finally iron, the star has built a significant portion of the periodic table. It has created, through patient nuclear transformations over millions of years, the chemical diversity necessary for planets, for minerals, for the complex chemistry of life. It has built, atom by atom, the material foundation of the world you inhabit. In the quiet depths of nuclear physics, there exists a profound truth, a fundamental limitation written into the structure of matter itself. This truth determines the fate of massive stars, sets the boundary between stellar life and death, and explains why the universe contains heavy elements at all. It centers on iron, ordinary iron, the metal of nails and blood cells, of planetary cores and ancient weapons, and on iron's extraordinary stability. To understand this, we must think about nuclear binding energy, about the forces that hold atomic nuclei together against the electromagnetic repulsion of their protons. Every nucleus represents a balance between the strong nuclear force, which pulls protons and neutrons together, and electromagnetic repulsion, which pushes protons apart. When nuclei fuse, combining lighter elements into heavier ones, the resulting nucleus is sometimes slightly less massive than the sum of its parts. This missing mass has been converted into energy. Following Einstein's famous equation, E equals mc, this is the energy that powers stars. But here is the key insight, the realization that explains everything that follows. This energy release is not uniform across the periodic table. As you build heavier and heavier elements through fusion, each step releases less and less energy per fusion event. The curve of binding energy rises as you move from hydrogen toward iron, meaning that each fusion reaction in this range releases energy. But at iron specifically, at iron 56, with 26 protons and 30 neutrons, the curve reaches its maximum. Iron 56 has the highest binding energy per nucleon of any element. It is the most stable nucleus in the universe. Beyond iron, the curve begins to descend. Fusing iron into heavier elements doesn't release energy, it consumes energy. This is why iron represents an insurmountable wall for stellar fusion, why a star cannot sustain itself by fusing iron into heavier elements. The fundamental thermodynamics of nuclear physics forbids it. Iron is the ash from which no energy can be extracted, the endpoint of fusion's power to drive stellar processes. Let us drift back into the heart of our massive star, to those final days when silicon burning is producing iron group elements at a furious rate. The iron core grows rapidly, accumulating mass from the silicon burning shell above it. This iron, like the lighter elements in the outer shells that are still undergoing fusion, is not a fuel source. It is waste, an accumulation of the most stable nuclei that cannot be further processed for energy. The core fills with iron the way a furnace fills with ash. Meanwhile, the star's outer layers continue their fusion processes, oblivious to the catastrophe brewing at the center. Hydrogen burns in the outermost shell, helium burns in the next shell inward, then carbon, oxygen, silicon, each layer producing energy, each layer contributing to the radiation pressure that holds up the star against its own gravity. But the iron core contributes nothing. It simply accumulates, growing denser and more massive with each passing hour. There is a critical threshold here, a limiting mass determined by the principles of quantum mechanics and relativity. This is the Chandrasekhar limit, named after who worked out in the 1930s that there is a maximum mass that can be supported by electron degeneracy pressure, the quantum mechanical pressure arising from the fact that electrons resist being compressed into the same quantum state. For an iron core, this limit is about 1.4 solar masses. As the core approaches this mass, as more and more iron accumulates from the silicon burning shell above, the star is racing toward a point of no return. The electrons in the core are already degenerate, packed as closely as quantum mechanics allows. The core cannot support additional mass through electron pressure alone. Yet the silicon burning continues, adding mass remorselessly, pushing the core toward the Chandrasekhar limit, and then, in a moment that defies human comprehension in its sudden violence, the core crosses the threshold. It can no longer support itself. Electron degeneracy pressure, which has been holding back the crushing weight of the star's outer layers, fails. The core begins to collapse. This is not a gradual process, not a slow sinking. This is free fall, catastrophic implosion. Matter falling inward at velocities that rapidly approach a significant fraction of the speed of light. The entire core, a sphere with a mass comparable to our Sun, collapses in less than a second. As it collapses, the density and temperature skyrocket. The iron nuclei, those most stable of elements, are torn apart in a process called photodisintegration. Photons, particles of light, have so much energy at these temperatures that they can break apart nuclei that are normally stable. The iron is destroyed, broken back down into helium nuclei, and then into individual protons and neutrons. This photodisintegration consumes tremendous energy that is no longer available to support the star. The collapse, the density becomes so extreme that electrons are forced into protons, combining to form neutrons and releasing neutrinos in the process. These neutrinos, ghostly particles that barely interact with matter, carry away enormous amounts of energy, further draining energy from the core, further accelerating the collapse. The core implodes until it reaches nuclear density, the density of an atomic nucleus, about 400 trillion times the density of water. At this point, the neutron degeneracy pressure finally halts the collapse. The core rebounds, like a ball of matter bouncing off an incompressible floor. A shockwave forms and races outward through the star's layers. This shockwave, carrying the energy equivalent to the Sun's entire lifetime output of energy released in seconds, blasts through the shells of silicon, oxygen, carbon, helium, and hydrogen. As it passes through each layer, it heats the material to billions of degrees. In this intense heat and pressure, a final burst of fusion occurs. Elements heavier than iron, gold, platinum, uranium, and all the other heavy elements that cannot be produced through normal fusion are created in seconds through rapid neutron capture. The shock wave sweeps up the stellar material and accelerates it to thousands of kilometers per second. It reaches the star's surface and breaks through. The star explodes, perhaps the most profound aspect of this iron wall. This fundamental limitation of fusion is that it transforms stellar death into cosmic creation. If stars could continue fusing elements indefinitely, if there were no endpoint to fusion's power, stars might burn forever, locking up elements in their cores indefinitely. But because of iron's stability, because fusion must stop at iron, massive stars are doomed to explode. And in exploding, they scatter their accumulated elements across the galaxy, enriching the interstellar medium with the periodic table, making possible the formation of new stars, planets, and perhaps life itself. There is something profoundly beautiful about this. About how a fundamental limitation in nuclear physics, a simple fact about binding energies, determines the fate of stars and, ultimately, the chemical evolution of the universe. The iron wall is both an ending and a beginning, both a limit and an opportunity. It marks the boundary between stellar life and death, but in dying, stars transcend their individual existence, becoming part of the larger cycle of cosmic chemical evolution. Their atoms disperse to form new worlds, new possibilities, new expressions of matter's endless potential for complexity and organization. There are moments in nature when forces that have been held in perfect balance for eons suddenly shift, when equilibrium gives way to catastrophe, when the patient architecture of millions of years dissolves in an instant. The core collapse of a massive star is one such moment, perhaps the most violent transformation that occurs in the everyday universe. An event of such concentrated intensity that it challenges our ability to comprehend what matter can do. Under extreme conditions, let us return to that iron core, grown now to perhaps 1.4 times the mass of our entire Sun, yet compressed into a sphere only a few thousand kilometers across. The density here is already extraordinary, millions of times denser than any material on Earth, denser than the center of our own Sun. With each cubic centimeter containing hundreds of tons of matter, the pressure is almost beyond imagining, the weight of the star's outer layers pressing down with a force that would instantly crush any ordinary matter into pure energy. For a brief time, the core has been supported by electron degeneracy, pressure, a quantum mechanical effect that arises from the Pauli exclusion principle. This principle states that no two electrons can occupy the same quantum state, which means that as you try to compress electrons together, they resist, not because of any force in the classical sense, but because quantum mechanics simply forbids them from being squeezed into the same configuration. It is, in a sense, the universe enforcing its own rules about how matter can be arranged. But this degeneracy pressure has limits. As the iron core grows beyond the Chandrasekhar limit of roughly 1.4 solar masses, the electrons are already compressed as much as quantum mechanics allows. The silicon-burning shell above continues, adding mass to the core. Inexorably, something must give, and what gives is the core itself. The collapse begins at the center, where the density and pressure are highest. Gravity overwhelms the electron degeneracy pressure. Matter begins falling inward, and once it begins, it accelerates with terrifying speed. The inner regions of the core reach velocities of 70,000 kilometers per second, nearly a quarter of the speed of light in less than a second. The entire collapse, from a sphere thousands of kilometers across to a sphere perhaps 20 kilometers across, occurs in less time than it takes to read this sentence. As the core collapses, several extraordinary processes occur simultaneously, each contributing to the catastrophe. The density rises so rapidly that photons, particles of light-type energies sufficient to disintegrate iron nuclei. This process, called photodisintegration, reverses billions of years of fusion in seconds. The iron 56 nuclei, each containing 26 protons and 30 neutrons, are broken apart into helium for nuclei. These helium nuclei are further broken down into individual protons and neutrons. It is as if the star's entire history of element building is being unwound, as if time itself is running backward through the periodic table. This disintegration consumes enormous amounts of energy that is no longer available to provide pressure support against gravity. Each iron nucleus that disintegrates absorbs about 124 million electron volts of energy. With countless nuclei being destroyed every instant, the energy drain is catastrophic. The collapse accelerates further. Meanwhile, as the density continues to climb, another process begins: electron capture. At normal densities, electrons and protons are stable. They don't spontaneously combine, but at the extreme densities in the collapsing core, electrons are forced so close to protons that they merge, combining to form neutrons and releasing electron neutrinos in the process. This process, sometimes called fundamentally changes the composition of the core, transforming it from a mixture of nuclei and electrons into nearly pure neutron matter. The neutrinos produced by electron capture are extraordinary particles in their own right. Neutrinos interact so weakly with matter that they can pass through the entire Earth without being absorbed. Under normal circumstances, even the dense matter of a stellar core is essentially transparent to neutrinos. They're produced in fusion reactions at the star's center and simply stream out into space, carrying away energy. But the collapsing core is not normal circumstances. The density becomes so extreme, so far beyond anything found in stable stellar matter, that even neutrinos begin to be trapped, unable to escape quickly enough. They diffuse outward through the ultra-dense matter over several seconds, an eternity in the timescale of the collapse. The core continues its catastrophic implosion. The density surpasses that of atomic nuclei. the density you would get if you could somehow remove all the empty space within atoms and pack the nuclei together directly. At this point, we have essentially created a single enormous atomic nucleus the size of a small city, a configuration of matter so exotic that it exists nowhere else in the universe except in neutron stars and, briefly, in the cores of collapsing massive stars. At this nuclear density, the neutron degeneracy pressure finally provides sufficient resistance to halt the collapse. Neutrons, like electrons, obey the Pauli exclusion principle and cannot be compressed beyond a certain point. The inner core reaches this limit and stops collapsing almost instantaneously. But the outer layers of the core haven't gotten the message yet. They're still falling inward at tens of thousands of kilometers per second. What happens next can only be described as a cosmic rebound. The infalling matter crashes into the incompressible inner core and bounces back. Like a ball being dropped onto an infinitely hard floor, a shockwave forms at the boundary between the inner core that has already bounced and the outer core that's still falling inward. This shockwave begins racing outward through the star's layers, carrying more energy than the sun will emit in its entire 10 billion year lifetime. But here's where the story becomes more complex than simply the star explodes. The shockwave, as it propagates outward through the still infalling material, loses energy. It has to do work to push matter outward against its inward momentum. And it loses energy to photodisintegration as it heats the material through which it passes. Within milliseconds, the shockwave begins to stall, losing momentum, no longer able to blast its way through to the star's surface. This is where the neutrinos become crucial. Trillions upon trillions of neutrinos are streaming outward from the protoneutron star at the center, carrying away the gravitational binding energy released by the collapse. About 1053 ergs, an almost incomprehensible amount of energy. Although neutrinos interact weakly with matter, the density of the infalling material is so high that some tiny fraction of these neutrinos are absorbed, and that tiny fraction of that enormous flood of neutrinos carries enough energy to revive the stalled shockwave. The shockwave begins moving outward again. Heated and pushed by neutrino energy deposition, it accelerates through the layers of silicon, oxygen, carbon, helium, and hydrogen, heating each layer to billions of degrees, initiating explosive fusion reactions, sweeping up stellar material and accelerating it to thousands of kilometers per second. After traveling through thousands of kilometers of stellar material, after overcoming the resistance of infalling matter, after being revived by neutrino heating, the shockwave finally reaches the star's surface and breaks through. In this moment of breakthrough, we witness the transformation of death into creation, of collapse into explosion, of ending into beginning. The shockwave emerges from the star's surface, accelerating the outer layers into space at tremendous velocities. The star, which has been building complexity for millions of years through patient fusion processes, suddenly releases the products of those processes to the cosmos. What was locked within the stellar core is now liberated, cast across light years of space, destined to enrich the interstellar medium, and perhaps billions of years later, to become part of new stars, new planets, new forms of matter's endless experimentation with organization and complexity. Imagine, if you can, a single star suddenly shining with the luminosity of an entire galaxy, 100 billion suns worth of light pouring from a single point in space, visible across millions of light years, brilliant enough that if one occurred in a nearby star system, it would be visible in daylight from Earth, casting shadows at midnight. This is a supernova, one of the most energetic events in the cosmos, a cosmic beacon, announcing both the death of a star and the birth of new possibilities. The explosion begins when the shockwave, revived by neutrino heating, breaks through the star's surface. The outer layers, suddenly unconfined, expand outward at velocities of 10,000 to 30,000 kilometers per second, up to 10% of the speed of light. The expanding material compresses and heats, reaching temperatures of billions of degrees. At these temperatures, the material emits intense radiation across the electromagnetic spectrum: gamma rays, X-rays, ultraviolet light, visible light, infrared, radio waves. The star brightens by a factor of billions within hours. For a brief period, perhaps a few weeks at peak brightness, this single dying star can outshine all the other stars in its galaxy combined. If you could observe a distant galaxy before and after a supernova, you would see the galaxy suddenly become noticeably brighter, with a brilliant new point of light appearing where there was nothing remarkable before. This is how supernovas got their name. Early astronomers thought they were witnessing the birth of new stars. Nova, meaning new in Latin, with super added later when it became clear these events were far more luminous than ordinary novae. The light we see from a supernova carries within it the story of the star's life and death. Spectroscopy, the analysis of light broken down into its constituent wavelengths, reveals which elements are present in the expanding debris. In the first days after explosion, we see primarily hydrogen and helium from the star's outer layers. As the debris expands and becomes more transparent, we begin to see deeper into the ejecta, revealing the products of nuclear burning: oxygen, silicon, sulfur, calcium. Sometimes, in the very brightest phases, we can detect the signatures of radioactive isotopes created in the explosion itself. Isotopes like nickel-56 and cobalt-56, which decay on timescales of weeks to months, their radioactive decay helping to power the supernova's luminosity long after the initial explosion. But the visible light, spectacular as it is, represents only a tiny fraction of the energy released in a supernova. The vast majority of the energy, perhaps 99% of it, is carried away by neutrinos in the first few seconds after core collapse. These ghostly particles stream outward from the newborn neutron star, carrying the gravitational binding energy released when the core collapsed from thousands of kilometers across to just 20 kilometers. If we had neutrino eyes instead of eyes that see visible light, we would see the neutrino burst arrive hours before the visible light, as the neutrinos race ahead of the shockwave, unimpeded by the star's layers. The kinetic energy of the explosion, the energy of the expanding debris, also enormous, about Ya-ergs, which is roughly equivalent to the sun's entire lifetime output of radiant energy. This kinetic energy drives the supernova remnant's expansion for thousands or even tens of thousands of years. The expanding shell of gas sweeps up the interstellar medium, compressing it, heating it, sometimes triggering the formation of new stars in the compressed regions. The shockwave propagating through space becomes a sculptural force, carving cavities in the interstellar medium, creating bubbles and filaments of hot gas, leaving behind structures that persist for millions of years. As the debris expands, it cools and becomes more transparent. Within days or weeks, the supernova fades from peak brightness. Within months, it becomes too faint to see with the naked eye. But telescopes can continue tracking it for years or even decades, watching as the expanding shell grows larger and fainter, eventually merging with the surrounding interstellar medium and becoming indistinguishable from it. Yet, this is not simply destruction, it is transformation, redistribution, enrichment. The elements created during the star's lifetime and in the explosion itself are now scattered across space. Carbon and oxygen from helium burning, silicon and sulfur from carbon and oxygen burning, iron from silicon burning, and a wealth of heavier elements from explosive nucleosynthesis. All of this is now mixing with the pristine hydrogen and helium of the interstellar medium, increasing its metallicity, its heavy element content. Consider what this means on galactic timescales. When the first stars formed in the early universe, perhaps 200 million years after the Big Bang, they were made of almost pure hydrogen and helium. These first-generation stars, sometimes called population 3 stars, contained virtually no heavy elements because none existed yet. But when these massive first stars exploded as supernovas, they enriched the surrounding gas with the first heavy elements. The next generation of stars formed from this enriched material, containing more heavy elements than their predecessors. This process has been repeating for over 13 billion years. Each generation of stars is born from gas clouds slightly more enriched than the previous generation. With each cycle of stellar birth, life, death, and explosion, the galaxy's heavy element content increases. Our Sun, formed about 4.6 billion years ago, is perhaps a second or third generation star, born from gas that had already been enriched by multiple generations of stellar death. The heavy elements in our solar system, the oxygen we breathe, the silicon in rocks, the iron in Earth's core, the calcium in our bones, all came from supernovas that exploded before our solar system formed. At the site of the explosion, something extraordinary often remains. A neutron star, or, if the progenitor was massive enough, a black hole. The neutron star is the collapsed core, an object with a mass of 1 to 2 suns, compressed into a sphere only 20 kilometers across. The density is almost beyond comprehension. teaspoon of neutron star material would weigh about 1 billion tons. Neutron stars can rotate rapidly, up to hundreds of times per second, and they often have intense magnetic fields, trillions of times stronger than Earth's magnetic field. If the magnetic axis is misaligned with the rotation axis, the neutron star can emit beams of radiation that sweep across space like lighthouse beams. We detect these as pulsars, regular pulses of radio waves, or other radiation ticking with clockwork precision. The supernova remnant itself evolves through several distinct phases over thousands of years. Initially, the ejecta expands freely, barely noticing the thin interstellar medium. Then, as it sweeps up more and more material, it begins to slow down. The shock wave heats the swept-up material to millions of degrees, creating an expanding shell of hot X-ray-emitting gas. Eventually, after thousands of years, the remnant cools and fades, its material mixing with the interstellar medium, indistinguishable from it, except perhaps for slight chemical peculiarities that record its origin in stellar death. And so the cycle continues. Gas clouds collapse to form stars. Stars burn and build heavy elements. Massive stars explode and scatter those elements, enriching the gas clouds from which new stars will form. It is a grand recycling process, operating on timescales of millions and billions of years, gradually increasing the chemical complexity of the universe, making possible the emergence of planets, of chemistry, of life. In this cosmic alchemy, death is inseparable from creation, ending inseparable from beginning, and the violence of stellar explosion becomes the gentlest prerequisite for existence itself. In the quiet moments just before a supernova explosion, when the shockwave is stalling and then being revived by neutrino heating, nature performs an act of creation that cannot occur anywhere else in the universe. In a span of seconds, literally seconds, elements heavier than iron are forged through processes of such intensity and improbability that they represent some of the most exotic nuclear physics we know of. This is the realm of explosive nucleosynthesis, and it solves one of the most important puzzles in our understanding of cosmic chemical evolution. We have seen how stars can build elements up to iron through fusion, how each successive stage of burning creates heavier and heavier elements, from hydrogen to helium to carbon to oxygen to silicon to iron. But the periodic table doesn't stop at iron. There are dozens of elements heavier than iron: copper, zinc, silver, gold, platinum, lead, uranium, elements that cannot be produced through normal fusion because such fusion would consume energy rather than release it. Where do these elements come from? The answer lies in neutron capture, in processes that occur during and immediately after core collapse, when the conditions are so extreme that nuclei can capture neutrons and build their way up the periodic table one neutron at a time. Let us explore how this works. Starting with the concept of isotopes. Each element is defined by the number of protons in its nucleus. Iron has 26 protons, gold has 79 protons, but nuclei can contain different numbers of neutrons while maintaining the same number of protons. These different configurations are called isotopes. Iron 56 has 26 protons and 30 neutrons. Iron 57 has 26 protons and 31 neutrons. Iron 58 has 26 protons and 32 neutrons. They're all iron, chemically identical, but with different masses. When a nucleus captures a neutron, it becomes a heavier isotope of the same element. If Iron 56 captures a neutron, it becomes Iron 57. If Iron 57 captures another neutron, it becomes Iron 58. But there's a limit to how many neutrons a nucleus can hold. Eventually, the nucleus becomes unstable and undergoes beta decay. Neutron converts into a proton, an electron, and an anti. The electron is ejected, but the proton remains, increasing the atomic number by 1. The iron nucleus has become a cobalt nucleus. This is how you can build heavier elements from lighter ones. Capture neutrons to move to heavier isotopes. Wait for beta decay to increase the atomic number. Then capture more neutrons, and so on, climbing the periodic table step by step. But this process requires a supply of free neutrons and enough time for the captures and decays to occur. Nature provides two distinct environments where this can happen, giving rise to two processes, the S process and the R process. The S process, or slow process, occurs in stable stars over long periods, thousands to millions of years. In certain types of evolved stars, particularly asymptotic giant branch AGB stars, nuclear, reactions produce free neutrons that can be captured by seed nuclei like iron. The neutron flux is relatively low, so nuclei capture neutrons one at a time, with plenty of time for beta decay to occur before the next capture. The S process can build elements up to bismuth, the heaviest stable element, but it proceeds through stable or long-lived isotopes, following a specific pathway through the chart of nuclides. But the S process alone cannot account for the abundances of all heavy elements we observe in the universe. Many neutron-rich isotopes that we find in nature cannot be produced through the slow neutron capture path because they lie on the neutron-rich side of stability, accessible only if neutron captures happen so rapidly that beta decay doesn't have time to occur between captures. This requires the R process, the rapid process. The R process occurs in environments with extraordinarily high neutron densities, where nuclei are bombarded with so many neutrons, so quickly that they capture dozens of neutrons in seconds before any beta decay can occur. The nuclei are pushed far to the neutron-rich side of the chart of nuclides, into regions of exotic, highly unstable isotopes that have never been produced in laboratories and whose properties we can only estimate from nuclear theory. For decades, the site of the R process was uncertain. Core collapse supernovas were the leading candidate, with the extreme conditions in the shockwave and in the neutron-rich material ejected from near the neutron star, providing potential sites for rapid neutron capture. More recently, another site has been confirmed: the mergers of neutron stars. When two neutron stars orbit each other and eventually spiral together and merge, they eject small amounts of neutron-rich material. This material, essentially pure neutron star matter expelled into space, provides ideal conditions for the R process. The 2017 detection of gravitational waves from a neutron star merger, along with the subsequent optical and infrared observations of the event, confirmed that such mergers produce R process elements, particularly gold, platinum, and lanthanides in both supernovas and neutron star mergers. The R process proceeds explosively. Seed nuclei, perhaps iron ore elements near iron are immersed in an overwhelming flux of neutrons. They capture neutron after neutron in rapid succession, becoming heavier and heavier isotopes, pushing far from stability. The nucleus might capture dozens of neutrons in a second. Eventually, the neutron flux subsides, the material expands and cools, the neutron density drops, and the captures stop. What remains are extremely neutron-rich nuclei. Far from the valley of beta stability, these nuclei now begin a process of radioactive decay, undergoing beta decay after beta decay, each decay converting a neutron into a proton and increasing the atomic number by 1. The nucleus slides back towards stability, climbing up in atomic number while decreasing in neutron number. This decay chain can last from seconds to millions of years, depending on the lifetimes of the intermediate isotopes. Eventually, the nuclei reach stable configurations, and we're left with stable, heavy elements: gold 197, platinum 295, lead 208, and many others, including the actinides like thorium and uranium. Consider gold, that precious metal prized by humans for millennia, used in jewelry, in electronics, in currency. Gold 197, the only stable isotope of gold, cannot be produced through normal stellar fusion. It requires the up. Every gold atom in existence was created in one of these extreme events, either in the final seconds of a supernova explosion or in the violent merger of neutron stars. The gold ring on someone's finger, the gold in the electronics of a smartphone, the gold reserves of national banks, all of it was forged in cosmic violence billions of years ago, created through rapid neutron capture in conditions of density and temperature that we can barely recreate, even in our most powerful particle accelerators. The same is true for uranium, the heaviest naturally occurring element, uranium-238 and uranium-235. The isotopes that power nuclear reactors and weapons were created through the R process. Their radioactive decay, with half-lives of billions of years, provides some of the heat that keeps Earth's interior molten, driving plate tectonics and maintaining the magnetic field that protects us from solar radiation. In a very real sense, the R process elements in Earth's core and mantle are still releasing the energy that was stored in them during their creation in stellar explosions billions of years ago. Perhaps the most beautiful aspect of explosive nucleosynthesis is how it complements the steady burning that occurred during the star's life. The star spent millions of years patiently building elements through fusion, layer by layer, from hydrogen to iron. But in the final seconds of its existence, in the catastrophic conditions of core collapse and explosion, it created an entire additional portion of the periodic table through neutron capture processes. The calm and the catastrophic work together, the patient and the explosive combine, to produce the full diversity of elements we find in nature. And so, as the supernova debris expands into space, it carries not just the carbon, oxygen, and iron created during stable burning, but also gold, silver, platinum, and uranium created in seconds of explosive nucleosynthesis. This enriched material mixes with the interstellar medium, ready to be incorporated into the next generation of stars and planets. The heavy elements in your jewelry, in your electronics, in the earth beneath your feet, all of them are testament to stellar death, to the creative power of cosmic violence, to nature's ability to forge complexity from catastrophe. As we drift deeper into understanding stellar explosions, a subtle but important distinction emerges. Not all supernovas are created equal. Just as stars themselves vary enormously in mass, temperature, and composition, the explosions that mark their deaths also vary in mechanism, luminosity, and the elements they produce. Astronomers classify supernovas into several types based on their spectra, the pattern of light they emit at different wavelengths, and these types trace back to fundamentally different physical processes. The classification scheme began empirically, with observers noting that some supernova spectra showed strong hydrogen lines, while others showed no hydrogen at all. Those with hydrogen were designated type 2, while those without hydrogen were called type 1. Further subdivisions emerged as more supernovas were observed and their spectra analyzed in detail. Type I was split into type Ia, type Iab, and type Ic, based on the presence or absence of silicon and helium lines. What emerged from this taxonomy is a picture of diverse explosion mechanisms, each contributing differently to the cosmic inventory of elements. The supernovas we have been exploring in detail. The core collapse, explosions of massive stars are type 2 supernovas. These are the deaths of stars born with at least 8 times the mass of our Sun. Stars that have gone through the full sequence of fusion stages, building an onion-like structure of shells with an iron core at the center. When the iron core collapses and rebounds, the resulting explosion is a type 2 supernova. The strong hydrogen lines in their spectra revealed that these stars retained their hydrogen-rich outer envelopes right up until the moment of explosion. Type 2 supernovas are further subdivided based on how their brightness changes over time. Type 2p supernovas, P4 plateau, maintain a relatively constant luminosity for an extended period, weeks to months, before declining. This plateau phase is caused by the recombination of hydrogen in the expanding envelope, which converts kinetic energy into radiated light. Type 2L supernovas L4 linear show a more rapid, linear decline in brightness without a pronounced plateau, suggesting that their hydrogen envelopes are less massive or have been partially stripped away before explosion. There is something almost peaceful about observing a type 2p supernova's light curve, watching it maintain that steady brightness for weeks, like the star holding its breath before the final fade. During this plateau phase, the expanding photosphere gradually cools from perhaps 10,000 degrees Kelvin to a few thousand degrees, transitioning through colors from blue-white to red as it cools, like a cosmic ember slowly dying. Type IBI and Type IC supernovas also result from core collapse, but in these cases, the progenitor star has lost its hydrogen envelope before exploding. Type IB supernovas show helium lines in their spectra, indicating that while the hydrogen is gone, a helium layer remains. Type IC supernovas show neither hydrogen nor helium. The star has been stripped down to its inner layers of carbon, oxygen, and heavier elements before core collapse occurs. These stripped envelope supernovas typically arise from stars in binary systems, where a companion star gravitationally strips away the outer layers, or from very massive stars that lose their envelopes through powerful stellar winds. But the most intriguing supernova type, and in many ways the most important for cosmic chemical evolution, is Type Ia supernova, with an entirely different mechanism that doesn't involve core collapse at all. Type Ia supernovas arise from white dwarfs, the dense remnants left behind when medium-mass stars like our Sun die. A white dwarf is supported by electron degeneracy pressure, the same quantum mechanical effect that temporarily supports the iron core before its collapse. For an isolated white dwarf, this represents a stable end state. It will simply cool and fade over trillions of years. But if the white dwarf is part of a binary system with a companion star, material from the companion can flow onto the white dwarf, gradually increasing its mass. As the white dwarf accretes matter, approaching the Chandrasekhar limit of 1.4 solar masses, its central density and temperature rise. Eventually, carbon fusion ignites, not gradually in the core as in a normal star, but suddenly, throughout much of the white dwarf nearly simultaneously. This is a thermonuclear explosion, fundamentally different from the core collapse mechanism. The white dwarf doesn't form a neutron star remnant, it is completely disrupted, blown entirely apart, with the explosive fusion converting a substantial fraction of its mass into iron peak elements. Type Ia supernovas are extraordinarily uniform in their peak luminosity, so uniform that they can be used as standard candles to measure cosmic distances. This uniformity arises because they all occur at approximately the same mass, the Chandrasekhar limit, and involve the same mechanism, thermonuclear explosion of carbon and oxygen. By measuring how bright a Type Ia supernova appears and comparing it to how bright it should be intrinsically, astronomers can determine how far away it is. This technique was used in the late 1990s to discover that the universe's expansion is accelerating, a discovery that earned the Nobel Prize and revealed the existence of dark energy. From a chemical evolution standpoint, Type Ia supernovas play a crucial role as iron producers. The thermonuclear explosion converts a large fraction of the white dwarf's carbon and oxygen into elements near iron: chromium, manganese, iron, cobalt, nickel. A single Type Ia supernova can produce more iron than a core collapse supernova. Over cosmic history, Type Ia supernovas have been responsible for producing much of the iron and iron peak elements we see in the universe today. Meanwhile, core collapse supernovas types 2Ib and Ic produce a broader range of elements. They contribute oxygen, silicon, and other products of stellar burning during the star's life, plus iron from silicon burning and the collapse, plus heavy elements from our process nucleosynthesis. They also leave behind neutron stars or black holes, compact objects that can themselves become sources of gravitational waves and high-energy radiation. The relative rates of different supernova types shape the chemical evolution of galaxies. In young galaxies with active star formation, core collapse supernovas dominate because massive stars evolve quickly and explode soon after formation. These early explosions enrich the interstellar medium with oxygen, carbon, and other products of massive star nucleosynthesis. Type Ia supernovas, which require longer timescales because they arise from lower mass progenitors in binary systems, become more important later in galactic history. Increasingly, the iron abundance relative to oxygen and other alpha elements formed by adding helium nuclei. Astronomers can read this history in stellar spectra. The ratio of iron to oxygen in a star's atmosphere tells us about the mix of supernovas that enriched the gas cloud from which that star formed. Stars with low iron-to-oxygen ratios were formed from gas, enriched primarily by core collapse supernovas early in galactic history. Stars with higher iron-to-oxygen ratios, like our Sun, formed later, after Type Ia supernovas had added more iron to the mix. There is something profound in this realization, that we can read billions of years of galactic history in the light from distant stars, that the elements we observe encode information about the types and timing of stellar deaths that occurred generations ago. Each star carries within its composition a record of the supernovas that enriched its birth cloud, a chemical memory of cosmic violence stretching back through time. As we contemplate these different types of stellar death, we see that the universe employs multiple pathways to create and distribute elements: core collapse supernovas from massive stars, thermonuclear explosions of white dwarfs, neutron star mergers. Each contributes its own characteristic blend of elements to the cosmic mix. Together, they have built the periodic table over billions of years, enriching the universe from its initial simplicity of hydrogen and helium to the complex chemical tapestry we see today, the foundation upon which planets form, chemistry emerges, and life becomes possible. The the supernova fades, its light diminishing over weeks and months until it becomes invisible to the naked eye. Just another faint point requiring telescopes to track. But the story is far from over. In fact, in many ways, it is just beginning. The debris from the explosion, enriched with the periodic table of elements forged during the star's life and death, is now expanding into space at thousands of kilometers per second, carrying with it the seeds of future complexity. This expanding shell of gas and dust sweeps through the interstellar medium like a cosmic wave, compressing, heating, and mixing with the material it encounters. The shock wave still carrying tremendous energy even as it spreads across light years, plows into clouds of pristine hydrogen and helium, clouds that have drifted through space perhaps since the early days of the galaxy. These collisions are transformative. The shock compresses the clouds, increasing their density. In regions where the density becomes high enough, gravity can overcome the thermal pressure and the clouds begin to collapse, fragmenting into smaller clumps that will become the seeds of new stars. In this way, stellar death directly triggers stellar birth. The same explosion that scattered elements across space also creates the conditions necessary for those elements to be gathered into new stellar systems. It is a beautiful irony that destruction and creation are not opposites but partners in an ongoing cosmic dance, each making the other possible. The enriched material doesn't spread uniformly. Instabilities in the expanding shell create dense knots and filaments, regions where the supernova ejecta clumps together, mixing more thoroughly with the interstellar medium in some places than others. Over thousands of years, the supernova remnant grows to tens or even hundreds of light years across. Its interior, a complex tapestry of shocked gas, magnetic fields, and cosmic rays high in energy particles, accelerated to nearly the speed of light by the shock wave's passage. These supernova remnants are visible across the electromagnetic spectrum. In radio wavelengths, we see synchrotron emission from electrons spiraling in magnetic fields. In X-rays, we see the hot plasma heated to millions of degrees by the shock waves. In visible light, we see glowing filaments, where the shock has energized atoms to emit characteristic colors: red from hydrogen, green from oxygen, blue from other elements. Famous examples like the Crab Nebula, the remnant of a supernova observed in 1054 AD, still glow brightly today, nearly 1,000 years after the explosion, their intricate structures revealing the complex physics of shock waves interacting with magnetized plasma. Eventually, after tens of thousands of years, the supernova remnant cools and fades, its material thoroughly mixed with the surrounding interstellar medium. The expanding shell loses its distinct identity, merging with the general background of gas that fills the space between stars. But the enrichment remains. The heavy elements scattered by the explosion are now distributed through a volume of space perhaps hundreds of light years across, available to be incorporated into whatever forms. Next in this region of the galaxy, consider what this means for galactic chemical evolution. A single massive star, exploding as a supernova, enriches perhaps 1 million solar masses of interstellar gas with heavy elements. Dozens or hundreds of new stars might eventually form from this enriched material. Each of those stars carries within it the chemical legacy of the star that died, incorporating its carbon, oxygen, iron, and all the other elements into new stellar systems. If any of these new stars have planets, as many do, those planets too will inherit the elemental diversity created by previous stellar generations. The enrichment is cumulative and ongoing. Over the lifetime of a galaxy, billions of years, countless generations of stars are born, live, and die. Each massive star that explodes adds to the heavy element content of the interstellar medium. The galaxy's metallicity, its fraction of elements heavier than helium, gradually increases over time. In the early universe, shortly after the first stars formed, the metallicity was essentially zero. In our region of the Milky Way today, about 2% of the mass is in elements heavier than helium, all of it produced by stars. This process varies across a galaxy. The inner regions, where star formation has been more intense and prolonged, tend to have higher The outer regions, where star formation has been less active, have lower Dwarf galaxies, with their lower star formation rates, generally have lower metallicities than massive galaxies. Astronomers can trace these patterns, mapping the chemical evolution of galaxies over cosmic time, reading in the elements the history of stellar birth, life, and death. Some of the enriched material doesn't simply mix with nearby gas, but is ejected from the galaxy entirely. Supernova explosions, particularly when many occur in close succession, can drive galactic winds, large-scale outflows of gas from the galaxy into the surrounding intergalactic medium. This process, called galactic chemical enrichment, spreads heavy elements beyond individual galaxies, seeding the intergalactic medium with the products of stellar nucleosynthesis. When this enriched gas later falls back into galaxies or is incorporated into smaller galaxies through mergers, it brings with it the chemical signatures of stellar death from other systems. Nebulae, vast clouds of gas and dust, illuminated by nearby stars or by their own internal processes, become particularly visible sites of this enrichment. Some nebulae are literally the expanding remnants of stellar explosions, like the Crab Nebula or the Veil Nebula. Others are star-forming regions, where enriched gas is collapsing to form new stellar systems, the compression heating the gas and causing it to glow. The colors of these nebulae, captured in spectacular images from telescopes like Hubble, encode information about their composition. Hydrogen glows red, oxygen glows greenish-blue, sulfur glows red, and so on. Each color is a signature of elements created in previous stellar generations. Perhaps most remarkable is the realization that this entire process, expansion, mixing, compression, collapse, star formation, operates as a self-sustaining cycle. Stars create the conditions for future star formation through their deaths. The heavy elements they produce enabled the formation of planets and, potentially, life. Those planets orbit the next generation of stars, themselves enriched by previous deaths, part of an ongoing cycle that has been repeating for over 13 billion years. As clouds of enriched gas collapse to form new stellar systems, they fragment into rotating disks around the forming stars. The heavy elements within these disks, silicon, iron, magnesium, and others, can condense into solid particles, dust grains that collide and stick together, growing larger through gradual accumulation. These dust grains become pebbles, pebbles become planetesimals, planetesimals become protoplanets, and eventually, over millions of years, planets emerge. Rocky planets like Earth are made almost entirely of heavy elements, iron and nickel in the core, silicon and oxygen in the mantle and crust, all of it recycled stardust from previous stellar generations. And so the cycle continues, endless and ongoing, stars forming from enriched clouds, living out their lives, dying and enriching the next generation. In this great cosmic recycling system, matter is endlessly reprocessed, reorganized, experimented with, as the universe explores the possibilities inherent in its own laws and initial conditions. The supernova debris expanding through space today will, in millions or billions of years, become part of new stars, new planets, new forms yet unimagined, continuing the story of matter's eternal transformation across the vast canvas of space and time. Let us turn now from the cosmic scale to the intimate, from the vastness of space to the interior of your own body, to the atoms that right now form your bones, your blood, your brain, the very fabric of your being. Each element in your body tells a story, traces a lineage back through time to specific stellar processes, specific types of stars, specific moments of creation in the cosmic past. Start with hydrogen, the most abundant element in your body by number of atoms, though not by mass. The hydrogen atoms in your water, in your organic molecules, in every cell, are truly ancient. Most of them were created in the first 3 minutes after the Big Bang, formed when the universe was hot and dense enough for protons and neutrons to combine into the simplest nuclei. Your hydrogen is primordial, unchanged since the universe's birth, now incorporated into the complex chemistry of life after more than 13 billion years of cosmic evolution. But nearly everything else in your body came from stars. Consider the oxygen that makes up about 65% of your body mass. The oxygen in your water, in your proteins, in your DNA, in your bones. This oxygen was forged in the cores of massive stars during helium burning, when 3 helium nuclei fused to form carbon, and some of that carbon captured additional helium to produce oxygen. Stars at least 8 times the mass of our Sun, burning in the stable phase of their lives, created the oxygen you're breathing right now. When those stars exploded as supernovas billions of years ago, they scattered their oxygen into space. That oxygen drifted through the galaxy, eventually becoming part of the cloud that collapsed to form our solar system. incorporated into Earth's early atmosphere and oceans, cycled through billions of years of geological and biological processes, and finally arrived in you. The carbon that forms the backbone of every organic molecule in your body, about 18% of your mass, has a similar origin. Carbon is also produced during helium burning in massive stars through the triple alpha process. That delicate reaction where 3 helium nuclei must come together in just the right way. Every carbon atom in your DNA, in your proteins, in your fats and carbohydrates, in the neurotransmitters that enable your thoughts, all of it was created in the cores of ancient stars that died before our sun was born. You are, quite literally, organized stardust, carbon-based life built from stellar ashes. Nitrogen, which makes up about 3% of your body and is essential for amino acids and DNA, requires even more specific conditions. Nitrogen is produced through the CNO cycle, carbon-nitrogen cycle in the cores of massive stars, and also through various other burning stages. Some nitrogen also comes from novae, smaller stellar explosions that occur in binary star systems. The nitrogen in your proteins, in the amino acids that build your muscles and enzymes, in the nucleotides that encode your genetic information, came from multiple stellar sources, combined and distributed through supernovas and other stellar mass loss processes. Now place your hand over your heart and consider the calcium in your bones. About 1.5% of your body mass, calcium is synthesized through oxygen burning in massive stars, occurring at temperatures around 1.5 billion degrees Kelvin in the late stages of stellar evolution. The calcium that gives your bones their rigidity, that allows your muscles to contract, that enables nerve signal transmission, was created in the penultimate burning stage of massive stars, just before they progressed to silicon burning and then collapsed into supernovas. Your skeletal structure is built from atoms forged in stellar cores operating at temperatures that would vaporize any ordinary matter instantly. The phosphorus in your DNA and in a T-petha molecule that powers cellular metabolism came from oxygen burning as well, produced through similar high-temperature nuclear reactions in massive stars. Without phosphorus, there would be no way to store and transfer genetic information, no efficient mechanism for energy transfer in cells. The phosphorus atoms that make your thoughts possible, that encode your genetic heritage, that power every cellular process, were all created in dying stars. And then there's iron, about 0.006% of your body mass, but absolutely crucial to your survival. The iron in your hemoglobin, the protein that colors your blood red and carries oxygen from your lungs to your tissues, has a particularly interesting origin. Some of it came from silicon burning in the final days of massive stars, created just before core collapse in the brief phase when silicon was fusing into iron peak elements. Some came from type Ia supernovas, thermonuclear explosions of white dwarfs that are particularly efficient iron producers. Every time your heart beats, it pumps iron atoms created in stellar fires through your cardiovascular system. Every breath you take is enabled by iron atoms that once resided in the cores of dying stars. Trace elements in your body tell equally fascinating stories. The copper in your enzymes came from supernova explosions, likely synthesized during the explosive burning that occurs when the shockwave passes through the star's layers. The zinc in your immune system cells, in your protein structures, came from similar processes. The iodine in your thyroid, essential for regulating metabolism, is a heavy element that required neutron capture processes, possibly the S process in GB stars or the R process in supernovas or neutron star mergers. Consider the magnesium in your cells, crucial for hundreds of enzymatic reactions. Magnesium is produced during carbon burning in massive stars at temperatures around 600 million degrees. The potassium that maintains your nerve function came from oxygen burning and supernova explosions. The sulfur in your proteins, part of crucial amino acids like cysteine and methionine, was synthesized during oxygen burning as well. Even the tiny amounts of heavier elements found in your body carry cosmic stories. Any gold in dental work or jewelry, any silver in antibacterial agents, comes from our process nucleosynthesis, created either in the final seconds of supernova explosions or in the violent mergers of neutron stars. These are literally the rarest atoms on Earth, created in the most extreme conditions the universe can generate, and yet here they are, occasionally incorporated into human bodies and human artifacts. There is something both humbling and elevating about this accounting. Your body is not a separate thing from the universe, is the universe reorganized. You are a temporary arrangement of atoms that have been cycling through the cosmos for billions of years. Atoms that have been inside multiple stars, scattered through space in violent explosions, drifting through interstellar clouds, incorporated into our solar system, cycled through Earth's geology and biosphere, and now assembled into the pattern that is you. Different parts of you came from different stellar sources. The hydrogen is primordial, nearly as old as the universe itself. The carbon, nitrogen, and oxygen came primarily from massive stars that lived and died in the first few billion years of our galaxy's history. The iron came from both core collapse supernovas and type Ia supernovas occurring over billions of years.
The heaviest trace elements came from the most extreme events supernova, explosions or neutron star mergers occurring sporadically throughout galactic history. You are not made from the death of a single star, but from the deaths of many stars, each contributing its own elements to the cosmic mix from which you were eventually assembled. Your body is a reunion of atoms that have been separated for billions of years. Atoms created in different stars at different times in different parts of the galaxy, brought together by chance and circumstance into this particular configuration. This arrangement that thinks and feels and wonders about its own origin. And when you cease to be, when your body returns to the earth, those atoms will continue their journey. They will be recycled through ecosystems, through geology, eventually perhaps even escaping Earth entirely through atmospheric loss or human space exploration, continuing the cosmic journeys that began in stellar cores billions of years ago. You are a temporary custodian of stardust, a brief chapter in the eternal story of matter transforming itself across the universe. The planet beneath your feet, solid and seemingly eternal, is itself a monument to stellar death, a sphere of accumulated stardust, compressed by gravity, heated by radioactive decay, constantly churning and recycling through geological processes that have operated for 4.5 billion years. Every rock, every mountain, every grain of sand, every drop of water in the oceans carries within it the legacy of multiple stellar generations, a cosmic inheritance that predates our solar system by billions of years. Earth's formation began about 4.6 billion years ago from a rotating disk of gas and dust surrounding the young sun. This protoplanetary disk was not made of primordial material from the Big Bang, had it already been, enriched by multiple generations of stellar death. The molecular cloud from which our solar system formed had been seeded with heavy elements by supernovas that exploded perhaps billions of years earlier. The debris gradually mixing with the interstellar medium, drifting from the galaxy, eventually finding its way into the cloud that would become our cosmic neighborhood. The composition of this cloud, about 98% hydrogen and helium, 2% everything else, reflects billions of years of stellar nucleosynthesis and chemical evolution. That 2%, seemingly insignificant, made all the difference. Without heavy elements from previous stellar generations, planets like Earth could not exist. There would be no silicon for rocks, no iron for the core, no oxygen for water and atmosphere, no carbon for organic chemistry. Rocky planets are, by definition, accumulations of heavy elements, and all heavy elements come from stars. As the protoplanetary disk evolved, the heavy elements condensed into solid particles, dust grains of silicon, iron, magnesium, and other refractory elements. These dust grains collided and stuck together through static electricity and weak gravitational attraction, growing larger. Dust became pebbles, pebbles became rocks, rocks became planet smalls, bodies, kilometers or tens of kilometers across. These planet smalls, through further collisions, grew into protoplanets, and finally, after perhaps 100 million years of violent accumulation, into Earth. The iron and nickel in Earth's core, about a third of our planet's mass, came from supernovas, created through silicon burning in the finer days of massive stars and scattered into space through explosive death. This iron sank to Earth's center early in our planet's history when the interior was molten, differentiating under gravity to form the metallic core we have today. That core, still liquid in its outer portion, generates Earth's magnetic field through its motion, shielding the surface from solar radiation and making the biosphere possible. Our very existence depends on iron created in dying stars billions of years ago. The silicate rocks of Earth's mantle and crust making up most of the planet's volume are primarily silicon and oxygen, with various other elements mixed in. Silicon was synthesized through carbon and oxygen burning in massive stars. The oxygen came from helium burning. Magnesium, aluminum, calcium, and other common rock-forming elements each have their own stellar origins, created in specific burning stages of massive star evolution. When you hold a rock in your hand, you're holding material that was forged at temperatures of hundreds of millions or billions of degrees, in stellar cores, operating under pressures that would crush atoms themselves billions of years before Earth existed. The water in Earth's oceans, covering about 70% of the surfaces, itself a product of stellar nucleosynthesis. Each water molecule contains one oxygen atom from helium burning in massive stars and two hydrogen atoms from the Big Bang itself. The oceans are a chemical combination of the universe's earliest and intermediate products, mixed together in vast quantities and maintained in liquid form by Earth's fortuitous distance from the Sun. The water you drink, the water in your cells, the water that makes up most of your body, connects you directly to both the universe's birth and the deaths of ancient stars. Earth's atmosphere, too, carries elemental signatures from stellar death. The nitrogen that makes up 78% of the atmosphere came from CNO cycle processing in stars and from supernovas. The oxygen that makes up 21%, the oxygen we breathe, the oxygen essential for complex life, came from helium burning in massive stars, released through supernovas, initially trapped in minerals and water, and then later released into the atmosphere by photosynthetic life over billions of years. The argon, carbon dioxide, and trace gases each have their own stellar origins, each tracing back to specific nuclear processes in specific types of stars. The radioactive elements deep within Earth, primarily uranium, thorium, and potassium, 40R, still releasing heat from their decay. Heat that was originally stored in them during an OW process, nucleosynthesis in supernovas or neutron star mergers billions of years ago. This radioactive decay provides about half of Earth's internal heat, driving plate tectonics, volcanic activity, and the geological cycles that have shaped our planet's surface for billions of years in a very real sense. Earth is still being warmed by energy released in stellar explosions that occurred before our solar system formed. Consider the implications. Plate tectonics, which refreshes Earth's surface, recycles nutrients, regulates climate through the carbon cycle, and creates diverse environments that may have fostered the evolution of complex life. Is partially powered by radioactive decay of elements created in the universe's most violent events. The R-process elements that enable this geological activity were created in seconds during supernovas or neutron star mergers, yet they continue releasing their energy over billions of years, driving processes that make Earth a living, changing world. The diversity of minerals on Earth, over 5,000 different mineral species, catalogued, reflects the diversity of elements created by stellar nucleosynthesis. Each mineral is a specific crystal structure made from specific combinations of elements. Quartz is silicon and oxygen. Feldspar adds aluminum, potassium, sodium, or calcium. Olivine contains magnesium and iron. Each of these elements came from different stellar processes. Silicon from carbon, oxygen burning, oxygen from helium burning, iron from silicon burning, magnesium from carbon burning, and so on. When geologists study rocks, they are reading records of stellar death written in crystalline form, or deposits concentrations of valuable minerals that humans mine for metals represent. Places where geological processes of concentrated elements created in stars. Iron ore is concentrated stellar iron. Copper ore is concentrated stellar copper. Gold deposits contain R-process gold from neutron star mergers or supernovas, concentrated by hydrothermal fluids or other geological processes. The entire mining industry is based on extracting and purifying stellar matter that geological activity has helpfully concentrated for us. Even the soil beneath your feet is stellar in origin. Soil is weathered rock, broken down by water, air, and biological activity, enriched with organic matter from living things, but all of it traces back to stellar nucleosynthesis. The silicon, the iron, the potassium, the phosphorus all created in stars. The organic matter in soil is made from carbon, nitrogen, and other elements that living things extracted from the environment. But those elements themselves came originally from stars. Earth is not unique in this stellar heritage. Every rocky body in our solar system tells the same story. The Moon, Mars, Venus, Mercury, the asteroids, the moons of the outer planets, all are accumulations of stellar products, differentiated and processed in various ways by their specific histories, but fundamentally made of stardust. When Apollo astronauts brought back lunar rocks, when Mars rovers analyze Martian soil, when we study meteorites that fall from the asteroid belt, we are always examining material with the same fundamental origin, elements created in stars that died before our solar system formed. The realization that Earth itself is a repository of stellar death, a collection point for elements created across billions of years of galactic history, adds a profound dimension to our relationship with our planet. We are not merely living on Earth, we are living on and within the accumulated remnants of countless stellar lives, on a world built entirely from recycled star matter, a world whose very existence depends on the willingness of previous stellar generations to die explosively, scattering their hard-won elements across the cosmos to be gathered again into new forms, new possibilities, new experiments in matter's endless capacity for self-organization and complexity. Throughout human history, the night sky has been a canvas of seemingly eternal constancy, the same stars in the same patterns, night after night, generation after generation. Yet occasionally, dramatically, this constancy is broken. A new star appears where none existed before, blazing brightly for weeks or months before fading away.
These transient lights in the heavens have been recorded by observers across cultures and centuries, and in their historical records, we find some of humanity's earliest encounters with the violent deaths of distant suns. One of the most remarkable of these historical supernovas appeared in the spring of 1006 AD in the constellation Lupus. Chinese astronomers recorded it as a guest star of unprecedented brightness, visible even in daylight, shining 3 times brighter than Venus at its most brilliant. Arab astronomers, European monks, and observers across the Middle East and Asia all documented this celestial visitor. For months, it dominated the southern sky, so bright that people could read by its light at night. Modern analysis suggests this was a type Ia supernova thermonuclear explosion of a white dwarf occurring about 7,200 light-years from Earth. Today, we can observe the expanding remnant of SN 1006 with modern telescopes, a delicate shell of gas still racing outward at thousands of kilometers per second, a ghostly echo of that brilliant medieval appearance. Less than 50 years later, in 1054 AD, another supernova appeared, this time in the constellation Taurus. Chinese and Japanese astronomers recorded it meticulously. It was visible in daylight for 23 days and remained visible to the naked eye at night for nearly 2 years. This was a core collapse supernova, the death of a massive star, about 6,500 light-years away. The remnant of this explosion is today known as the Crab Nebula, one of the most studied objects in astronomy. At its center lies a pulsar, rapidly rotating neutron star spinning 30 times per second. The collapsed core of the exploded star, still emitting beams of radiation that sweep across space like a cosmic lighthouse. The Crab Nebula is particularly valuable to astronomers because we know exactly when the explosion occurred, allowing us to study how supernova remnants evolve over known timescales. The nebula is still expanding, still energized by the central pulsar, still emitting across the electromagnetic spectrum from radio waves to gamma rays. Filaments of gas glow in characteristic colors: red from hydrogen, blue-green from ionized oxygen, tracing the complex structure created by the explosion and subsequent interactions with the pulsar's intense radiation and magnetic field. For centuries after 1054, no supernova appeared close enough to be visible to the naked eye. The night sky returned to its apparent constancy. Supernovas surely continued to occur in distant galaxies, but without telescopes, humanity couldn't observe them. Then came 1572, when Tycho Brahe observed a supernova in Cassiopeia, and 1604, when Johannes Kepler documented another in Alpha. These observations helped shatter the Aristotelian notion that the heavens were perfect and unchanging, demonstrating that stars themselves could appear, brighten, and fade, that even the cosmos was subject to transformation and death. But for nearly 4 centuries after Kepler's supernova, no supernova appeared in our own galaxy or its immediate neighbors close enough to be visible without telescopes. Astronomers studied supernovas in distant galaxies, learning to classify them, understanding their mechanisms, using them to probe cosmic distances. The science of supernovas advanced tremendously during this time, yet all observations were of events occurring millions or billions of years ago, their light only now reaching Earth after crossing vast cosmic distances. Then, on February 23, 1987, a supernova appeared in the Large Magellanic Cloud, a small satellite galaxy of the Milky Way, located about 168,000 light-years away. SN 1987A, as it became known, was visible to the naked eye from the southern hemisphere and immediately became one of the most intensely studied astronomical events in history. For the first time, modern instruments, telescopes spanning the electromagnetic spectrum, neutrino detectors, computers for data analysis, could observe a relatively nearby supernova from its initial brightening through its subsequent evolution. SN 1987A provided extraordinary insights. Neutrino detectors in Japan and the United States captured the burst of neutrinos released during core collapse, just a handful of detections, but enough to confirm theoretical predictions about neutrino emission during stellar collapse. This marked the first time neutrinos from an astronomical source beyond the Sun had been detected, opening the field of neutrino astronomy. The detection occurred about 3 hours before the visible light from the explosion was observed, precisely as theory predicted, since neutrinos escaped immediately while the light had to propagate outward through the star's layers. Observations of SN1987A revealed unexpected complexities. The progenitor star, Sanjalac -69202, was a blue supergiant rather than the red supergiant typically expected for core collapse supernovas. The light curve showed unusual features, including a plateau phase and multiple peaks. As the debris expanded and became transparent, astronomers could observe the radioactive decay of nickel-56 and cobalt-56 created in the explosion, directly confirming theoretical predictions about explosive nucleosynthesis. Over the decades since 1987, telescopes have continued monitoring SN1987A's evolution. The expanding debris has crashed into material that the progenitor star ejected during its lifetime, creating a spectacular ring system that glows as the shockwave heats it. At the center, astronomers search for signs of the neutron star or black hole that should remain, though it has proven elusive, hidden perhaps behind dust or dimmed by some unexpected mechanism. Modern supernova surveys discover hundreds of supernovas every year in distant galaxies, using automated telescopes that repeatedly image large swaths of sky, searching for new points of light that weren't present in previous observations. These surveys have revolutionized our understanding of supernova diversity, revealing that stellar explosions are more varied than previously recognized, with Type Ia supernovas showing subtle differences in brightness and spectrum. Core collapse supernovas displaying a wide range of properties depending on progenitor mass and metallicity, and rare exotic events like superluminous supernovas pushing our theoretical understanding to its limits. Space telescopes have added new dimensions to supernova studies. Hubble has imaged supernova remnants in exquisite detail, revealing intricate structures invisible from ground-based observations. Chandra and XM Newton X-ray telescopes observe the hot plasma in supernova remnants, tracing the shockwaves and high-energy processes. The Fermi Gamma Ray telescope has detected gamma rays from supernova remnants, providing evidence that they accelerate cosmic rays to tremendous energies. Each wavelength reveals different aspects of these complex events, building a comprehensive picture of stellar death. Gravitational wave detectors like LIGO have opened yet another window on stellar death. While core collapse supernovas themselves produce gravitational waves too weak to detect at current sensitivities, neutron star mergers, which we now know can produce some of the heaviest elements through our process, nucleosynthesis, have been detected multiple times. In 2017, LIGO detected gravitational waves from a neutron star merger, and optical telescopes quickly identified the associated kilonova, an explosion powered by radioactive decay of our process elements. This multi-messenger astronomy, combining gravitational waves, electromagnetic observations, and theoretical modeling, represents the cutting edge of how we study extreme cosmic events. The historical supernovas and modern observations together paint a rich picture of stellar death across different times and distances. From the naked eye observations of medieval astronomers to neutrino detections and gravitational wave astronomy, each generation of observers has added new layers of understanding. We now know not just that stars explode, but how they explode, what conditions produce different types of explosions, what elements they create, how their remnants evolve, and how their deaths enrich the cosmos with the seeds of future complexity. The night sky above us contains countless stars approaching the ends of their lives, massive suns that will, inevitably, reach the iron wall and collapse into catastrophic explosion. Some are close enough that when they explode, if they explode during human civilization's existence, they will become spectacular visible events, perhaps rivaling the historical supernovas of 1006 and 1054, perhaps even surpassing them. These stellar time bombs tick away on cosmic timescales, their exact detonation times uncertain, but their ultimate fate sealed by the physics of massive stars. The most famous supernova candidate is Betelgeuse, the bright red star marking the shoulder of Orion, visible to anyone who looks up on a winter evening in the northern hemisphere. Betelgeuse is a red supergiant, a star that began its life with perhaps 15 to 20 times the mass of our Sun and has now swollen to enormous size. If placed at the Sun's position, it would extend beyond the orbit of Mars. This swelling indicates that Betelgeuse has exhausted its core hydrogen and is now in later evolutionary stages, fusing heavier elements in its core and shells. Betelgeuse is approximately 550 light-years away, close by astronomical standards, though far enough that its explosion would pose no danger to Earth. When Betelgeuse explodes, and astronomers believe it will, possibly within the next 100,000 years, a mere instant in cosmic time, though potentially well beyond human civilization's current span, it will become one of the brightest objects in Earth's sky. Estimates suggest it might reach an apparent magnitude of -12, comparable to the full moon, bright enough to cast shadows at night and be easily visible during daylight. This spectacular display would last for weeks or months before gradually fading over several years. Recent observations of Betelgeuse have heightened interest in its potential explosion. In late 2019 and early 2020, the star dimmed dramatically, losing more than half its brightness, a phenomenon called the Great Dimming. Some speculated this might signal imminent collapse, though subsequent observations revealed the dimming was likely caused by a massive cloud of dust ejected by the star, temporarily blocking our view of its photosphere. While this event wasn't the precursor to explosion, it reminded us that Betelgeuse is an active, evolving star in its final evolutionary phases, a star that could explode at any moment on cosmic time scales tomorrow or 100,000 years from now. We simply cannot predict with current knowledge. Other supergiant candidates populate our galactic neighborhood. Antares, the bright red star in Scorpius, is another red supergiant, roughly 550 light-years away, with about 15 solar masses. Ras Algethea in Hercules, Musephi in Cepheus. Multiple red supergiants within a few thousand light-years could potentially explode during human timescales. Each would produce a spectacular celestial show, though none quite as dramatic as Betelgeuse, due to either greater distance or lower luminosity. Eta Carini represents a different kind of supernova candidate, not a red supergiant, but a luminous blue variable, one of the most massive stars known, with perhaps 100 times the Sun's mass, located about 7,500 light-years away. Eta Carini is so massive that it's close to the theoretical upper limit for stellar mass. In the 1840s, it underwent a massive eruption, briefly becoming the second brightest star in the night sky, ejecting several solar masses of material in what's called a supernova impulsor event, a violent mass loss episode that mimics some aspects of a supernova but leaves the star intact. Eta Carini is highly unstable, likely to explode as a supernova within the next million years, possibly much sooner. When it does explode, despite its greater distance, it might be even more spectacular than Betelgeuse, potentially reaching magnitude -4 or bright as Venus at its best. Some models suggest it could even become briefly visible in daylight, a blue-white point of light competing with the sun. What would it be like to witness a nearby supernova? Imagine looking up one evening and seeing a bright new star where none existed before. A point of light that wasn't there yesterday but now outshines everything except the moon. Over the following nights, it brightens further, changing color subtly as its spectrum evolves, dominating the sky. For weeks, you could read by its light at night. Telescopes around the world would track its every change, measuring its spectrum, monitoring its evolution, while neutrino detectors would have captured the burst hours before the light arrived, and gravitational wave detectors would search for signals from the core collapse. Such an event would be a scientific bonanza, providing data about stellar death from a nearby source with modern instruments. We would learn more from one nearby supernova observed with current technology than from all the distant supernovas observed to date. The light curves, spectra, and neutrino signals would constrain theoretical models. The expanding debris would be resolved in unprecedented detail. Over decades and centuries, we could watch the supernova remnant evolve in real time, rather than inferring its evolution from observations of different remnants at different ages. Yet, despite the anticipation, we must acknowledge uncertainty. Massive stars in their final phases are extraordinarily complex systems, with convection, pulsation, mass loss, and nuclear burning occurring in intricate patterns that we don't fully understand. Predicting exactly when a star will explode is currently impossible. Betelgeuse might explode tomorrow or in 100,000 years. We simply don't know. Some astronomers search not just for explosion, but for precursors, observable changes that might signal a star's imminent collapse. Subtle changes in luminosity, Mass loss rate, neutrino emission, or other properties might provide hours, days, or weeks of warning before explosion. Networks of telescopes and detectors stand ready to respond to such signals, prepared to observe the explosion from its earliest moments through its subsequent evolution. The statistical rate of supernovas in our galaxy suggests we should expect several per century, but dust in the Milky Way's plain obscures many potential events. The last confirmed supernova in our galaxy was Kepler's in 1604. We're overdue for another, statistically speaking. Though overdue on cosmic timescales means little, the next galactic supernova could occur tomorrow or centuries from now. When the next nearby supernova finally occurs, it will be a moment of convergence between the cosmic and the human, between the ancient process of stellar death and modern scientific observation, between the objective phenomenon and the subjective experience of witnessing it. For a brief time, the night sky will display directly, visibly, dramatically, what is normally hidden across vast distances, the transformation of stellar death into cosmic creation, playing out in real time above our heads, a reminder that the universe remains dynamic, violent, and creative, constantly recycling its matter through the deaths and births of stars, and that we are fortunate enough to live in an era where we can understand, at last, what we're witnessing. As we approach the end of this gentle exploration, let us rest for a moment in the profound realization that has emerged through our journey, a realization that reshapes our understanding of who and what we are, that dissolves the apparent boundary between self and cosmos, that reveals the deep time and cosmic process written into the very substance of our being. You are not merely in the universe. You are the universe, a localized expression of cosmic matter and energy, temporarily organized into the pattern of a living being, capable of thought, of wonder, of understanding. Every atom in your body is a messenger from the distant past, carrying within it the history of stellar birth, life, and death, connecting you intimately to processes that occurred billions of years before you existed, across distances so vast that light from those stellar furnaces traveled for eons to reach the gas cloud that would eventually become our solar system. The calcium in your bones was forged at temperatures of billions of degrees in the final days of massive stars. The iron in your blood was created in stellar cores operating under pressures that would crush ordinary matter into plasma. The carbon in your DNA, the oxygen you breathe, the nitrogen in your proteins, all of it came from stars that died catastrophically, scattering their hard-won elements across the cosmos in explosions that briefly outshone galaxies. You are, quite literally, animated stardust, organized into a form that can contemplate its own cosmic heritage. This realization is more than a scientific curiosity. It speaks to something fundamental about the nature of existence. The universe is not a dead clockwork mechanism with life as an accidental afterthought. Rather, the universe is a creative process, constantly experimenting with organization and complexity, building from simplicity toward intricacy through the patient work of billions of years. Stars are not merely objects of distant beauty, but essential participants in this process, engines of chemical enrichment, without which the complex chemistry of life could never emerge. Consider the improbability and necessity of your existence. You required the Big Bang to create hydrogen. You required the first generation of massive stars to forge carbon, oxygen, and other light elements through fusion. You required those stars to explode as supernovas, scattering their elements into space. You required subsequent generations of stars to enrich the interstellar medium further, adding iron and heavier elements. You required the gravitational collapse of an enriched gas cloud to form our solar system. You required the accumulation of rocky material into Earth. You required billions of years of geological evolution to create a stable, habitable planet. You required the emergence and evolution of life over billions more years. And finally, you required the specific circumstances of your own conception and development. Every step in this chain was necessary. Break any link and you would not exist. This does not mean the universe was designed for you, Ritha. It means you are a product of the universe's creative capacity, one expression among countless others of what matter can do when given time, energy, and the right conditions. The universe has been working for 13.8 billion years to create the conditions for your existence, not through intention, but through the blind operation of physical law on cosmic scales. In this light, the death of stars takes on a different meaning. What might initially seem like tragedy or waste, massive stars living only millions of years before destroying themselves in violent explosions, reveals itself as generosity, as creative sacrifice. Stars do not die in vain. Their deaths are transformative, enriching the cosmos with the seeds of future complexity.
Without stellar death, without supernovas, there would be no heavy elements, no planets, no life, no consciousness, no one to ask why stars explode, or to understand the answer when it comes. The cycle continues even now. Stars in our galaxy and beyond are burning, building elements, approaching their explosive ends. When they explode, they will scatter new elements across space, enriching the interstellar medium from which future stars and planets will form. Perhaps billions of years from now, some of the atoms in your body, atoms that have already been inside multiple stars, will be incorporated into another star system, another planet, perhaps another form of organized complexity that we cannot now imagine. There is comfort in this continuity, in knowing that we are not separate from nature, but expressions of it, that the same laws and processes that govern galaxies also govern the beating of our hearts, that we are connected through our very atoms to the farthest reaches of space and the deepest recesses of time. We are not visitors to this universe. We belong here as surely as stars belong, as surely as galaxies belong, because we are made of it, through and through. Modern astrophysics has given us a gift, the knowledge of our cosmic origins, written in starlight and understood through decades of patient scientific work. This knowledge need not diminish our sense of meaning or significance. Instead, it can deepen it, showing us that we are part of something vast and ancient and ongoing. That the universe is not a static backdrop to our lives, but an active, creative process in which we participate. When you look up at the night sky, you are not looking at something distant and separate. You are looking at your source, at the stellar furnaces that created the elements of your body, at the cosmic environment from which you emerged. The stars are not merely beautiful, they are family, ancestors in the most literal sense, the progenitors without which you could not exist. And perhaps most remarkably, you are the universe become conscious of itself. Through your eyes, through your mind, the cosmos observes its own grandeur. Through your scientific understanding, the universe comes to comprehend the mechanisms by which it creates complexity and meaning. Every time you learn something about the universe, every time you pause to wonder at the night sky, or to understand a new concept in astronomy or physics, you are participating in something extraordinary. The universe is his ongoing project of self-discovery. As our exploration comes to its gentle close, carry with you this awareness. You are stardust, contemplating stars. You are the universe in human form, temporary but precious, part of an unbroken chain of matter and energy transformation stretching back to the universe's birth and forward to its unknowable future. The atoms of your body have witnessed the birth and death of stars, have drifted through interstellar space, have been recycled countless times through geological and biological processes, and now find themselves arranged in the improbable pattern that is you thinking, feeling, wondering, understanding. In this understanding lies not alienation, but belonging, not insignificance, but profound connection. We are brief expressions of cosmic matter, localized concentrations of stellar death and stellar birth, temporary but aware, small but conscious, ephemeral but meaningful. And in our brief time of existence, we have the extraordinary privilege of understanding where we came from, of seeing ourselves as part of the grand cosmic story, of recognizing in the death of distant stars the source of our own existence. Rest now in this knowledge, this cosmic kinship, this deep belonging,